Polar and nonpolar covalent bond, or can also be referred to as bond polarity. So what is a polar and a nonpolar covalent bond? If we recall from our previous lecture, covalent bonds are bonds that are formed due to the sharing of electrons between two atoms. For an example, let's say here we have an atom A with an unpaired electron in its orbital. And atom B, same thing, it has an unpaired electrons in its orbital. And now, both A and B do not have an octet of electrons, so they're not happy. So therefore, we can see that they would like to come together and share the electron to form a bond. And so here, A and B share the electron to form a bond right here. And this bond is then known as the covalent bond. So again, we see the covalent bonds are bonds that are formed due to the sharing of electrons between the two atoms. So many times, this bonding electron right here, so this electron, are not shared equally between the two atoms. And covalent bond where the electrons are not shared equally, we would refer to them as a polar covalent bond. Whereas covalent bond where the electrons are shared equally, we call them nonpolar polar covalent bond. For an example, in this scenario right here, if we were to have a pair of electrons that are shared equally between atom A and atom B, and here in this case, we indicate that by putting the electron between the two atoms. So in this case right here, A and B are sharing the electron equally. So here we have equal sharing of electron. If A and B are sharing the electron equally, we will refer to this covalent bond right here as a nonpolar covalent bond. And in another example, let's say here we have the bond between X and Y. In this case right here, I am putting the electron closer to the atom Y than the atom X to indicate that this have the unequal sharing of electron. Sharing of electron. If we were to have this case right here, this covalent bond between X and Y would then be referred to as a polar covalent bond. And anytime that we have a polar covalent bond, the bond is then said to be polarized, and it has something that we call a dipole moment. So here in this case right here, going back to the bond between X and Y, this is a polar covalent bond. And anytime that we have a polar covalent bond, there is a dipole moment. And to show this dipole moment right here, we will be representing that by drawing an arrow. Follow on the other end, we can see that it has something that looks like a half of a positive charge. So here in this case right here, the bonding electrons are shifted toward the atom Y than the atom X. And anytime that we have unequal distribution of electrons, the bond is then said to be a polarized bond, and it now have a dipole moment. So we would represent that again by drawing this arrow right here to represent the dipole moment. And we would always draw the dipole moment parallel to the direction of the bond and pointing to whichever atom that now has the electron shifted to it. So here in this case, the electron density are not shared equally between X and Y, but more to the atom Y. And because atom Y is now getting the electrons, and we know that electrons are negatively charged, so therefore the atom Y is then said to be partially negative. So this is the symbol of partial followed by negative. And X is losing the electrons, so therefore it becomes something that we call partially positive. So anytime we draw the dipole moment, the ends where we have this half of a positive charge right here, whichever atom on that side will be partially positive, and the atom on the other side of the arrow that is having the arrow pointing to it will then become partially negative. So What is bond polarity? Bond polarity is basically a measure of the degree in inequality in the sharing of electron between two atoms in a chemical bond. So if we go back to this example here, the bond between atom A and B, this have equal sharing of electron. So therefore, this bond right here is nonpolar covalent, or sometimes we simply say nonpolar. And therefore, because this have electron share equally, so therefore there is no net dipole moment or no dipole moment. If we were to be now looking at the another example, the bond between atom C and D. So here in this case right here, the electron are slightly shifted to atom D a little bit. So it does have a slightly small degree of unequal sharing in the electron. And in this case, shifting to the atom D. So therefore, it will have a small dipole moment. And we will draw that by drawing a small dipole moment pointing to the atom D. And in this case right here, since D, the atom D is gaining slightly a small amount of electron, it becomes partially negative, and now this will become partially positive. But the signs of this partial negative and positive are small because it only slightly unequal. So again, this is slightly unequal in sharing of electron. And therefore, we have a small dipole moment. And if we were to go back to another example between X and Y again, so here in this case right here, there is a high degree of unequalness in sharing of electron. So very much shifted to atom Y. So we would draw the dipole moment in here, and in this case, it would be a big dipole moment to say electron are shifted heavily to the Y atom. And now it would have a much bigger positive and bigger positive sign. So we have this one, it would be highly unequal in sharing of electron. And therefore, there will be a large dipole moment on this bond. So, why bond polarity? Where did this bond polarity come from? And the answer lies in a topic that is really important that we refer to as electronegativity. Now again, electronegativity is a really important topic here in chemistry. And a lot of time, this topic right here is the underlying explanation for the many behavior that we see in chemistry. So make sure you know what electronegativity is and understand where it's come from. So first, let's define electronegativity before we go over where does it come from. So electronegativity, abbreviated with EN, refer to the ability to attract the bonding electron pair to itself. So some atoms have higher ability to attract the bonding electron to itself. And if that is the case, we would then say that that atom would have a high electronegativity. And the reason why some atoms can attract the bonding electron to themselves better than the other is because that atom have more proton in its nucleus. And we know that because protons are positively charged, therefore between two atoms, if an atom would have more proton than the other, it will be able to attract the bonding electron to that atom better. And therefore, as the consequence, the bonding pair electrons is not shared equally between the two atoms, but slightly shifted to the atom that have more proton in its nucleus. And therefore, the bond is then said to be polarized. So here is a table right here where we are listing all of this value on this periodic table, and this value that you see in here are then called the electronegativity value. And all of this value right here was actually quantified by a chemist, very famous chemist named Linus Pauling, and he actually won the Nobel Prize in chemistry for the study of this electronegativity value. So Linus Pauling quantified the electronegativity value for all of the elements as follows. And here in this case right here, it ranges anywhere between 0 to 4. And 4 is one of the highest electronegativity value that an atom can have. And the higher the value, then that means the atom have high ability in attracting electron to itself. Now, it's important that we understand the trends in this electronegativity. So if we were to be looking at some of this element going from boron, its electronegativity is 2.0, carbon is 2.5, and nitrogen is 3.0, oxygen is 3.5, and fluorine is 4.0. So clearly, we see a trend right there. And if we were to now look at Be, which is 1.5, and lithium at 1.0, so we see that as we go from left to right on the periodic table, then the electronegative value of the elements are increasing by 0.5. So it's quite easy to remember. And in fact, it's important that we know electronegativity, but we will not be asking students to remember all of the electronegative value. However, we need students to understand the trends of how the electronegativity are increasing or decreasing. And my advice is for you to remember one electronegative value, which is to remember the electronegativity of carbon. Why carbon? Carbon is a very common types of element that you will see in organic chemistry and in more chemistry classes. So therefore, it's good to remember that value. And once we remember the electronegativity of carbon is 2.5, going to the right of carbon, it is increasing by 0.5. And going to the left of it, it is decreasing by 0.5. So therefore, we'll be able to figure out all of this electronegative value. Now, let's understand why. Why do the trends of electronegativity increase going from left to right? So if we still recall from the quantum mechanical model, all of in the periodic table, all of this element right here are on the same row, the second row of the periodic table. So that basically means that all of the valence electrons that this atom have are then located on the second principal shell. And as we go from left to right, then all of the electrons are still on the second principal shell, which in terms of distance from the nucleus, they are about the same. However, in the case as we go from left to right, we can see now that the element on the right side have more proton in the nucleus. So therefore, they will be able to attract the electron from the second principal shell better, and thus make those electrons come closer to its nucleus. So that's why that the trends is increasing from left to right. And also, this correlates to the size of the atom as well. The size is also decreasing as we go from left to right. And as the size decreases, that means that the electrons are closer to the nucleus. So this atom right here, it is smaller, and therefore it can attract the bonding electron better to itself. And now, as we go from top to bottom, the electronegativity is decreasing. Going from fluorine to chlorine, it goes from 4.0 to 3.0. Going from oxygen, it is 3.5 to sulfur, 3.5. Going from nitrogen, 3.0 to phosphorus, 2.1. So we see that as we go from top to bottom, it decreased by about 1 electronegative value. Now, but it does not extend the same thing as we keep going down further. So please remember that and understand that. So first, electronegativity increase going from left to right and decrease from top to bottom. Now, why there it decrease from top to bottom? Well, the answer has to do with size as well. The element on the bottom are bigger, and because they're bigger, the bonding electron would then be further away from its nucleus. So therefore, it will not be able to attract those electrons as well, and thus having a low electronegative value. Now, we can use electronegative value to figure out whether a bond is polar or nonpolar. How will we be able to do that? The answer is by looking at the electronegativity difference. Anytime we have a bond between two atoms, and each of the atoms has a particular electronegative value, we want to know what is the differences in electronegative value between the two atoms. If two atoms have very similar electronegative value, meaning the difference between them was equal to 0, so both of the atoms have equal ability in attracting the bonding electron to themselves. So thus the electron would then be shared equally between the two atoms. And thus the bond would then be a nonpolar covalent bond. Now, if we were to now have a bond between two atoms with a difference in electronegativity of 0.5 or higher, then that now means one atom has more or higher ability to attract the bonding electron to itself more than the other. So in that case right there, the electron will not be shared equally between the two atoms, but shifted to the atom with a higher electronegative value. So in that case, we will then have the polar covalent bond. If the differences between two atoms in the electronegativity is really high, for example 2.0, that means one atom really wants the electron much more than the other. So therefore the atom that is more electronegative will be able to steal or pull the electron from the other atom to it, in which that the electron would then be transferred to the atom of higher electronegativity. And if that is the case, then now we see the transfer of electrons, and the bond that we see will then be the ionic bond. So for the most part, this is how we can remember it. If the difference in electronegativity is from 0 to 0.4, the bond would then be a nonpolar covalent bond. But if the differences between electronegativity between two atoms is 0.5 to about 1.5, then for the most part, that bond will be classified as a polar covalent bond. And if we were to now have differences in electronegativity that is about 1.5 or up to 2 point something or higher, then now for the most part, that bond would be considered as an ionic bond or a very polar covalent bond. And in the end, we see that the bigger the electronegativity difference, the more polar the bond would be. Let's now try some of the example to make sure that you have understood this concept. So here in this case right here, you are asked to rank the bond below in order of increasing polarity. So which one would then be most polar and which one would be the least? And if we were to have a polar covalent bond, we would need to determine the direction of the polarity of the bond by drawing the dipole moment. And then lastly, classify the bond whether it is polar or nonpolar or ionic. So first example, a bond between nitrogen and chlorine. What kind of bond would it be? So first, we now need to go back to the electronegative value. And if we were to look on this table from above, we can see that nitrogen has an electronegative value of 3.0. And for chlorine, it is 3.0 as well. So let's write that down. So the electronegativity of chlorine is 3.0, and nitrogen is also 3.0 as well. So the difference in electronegativity, delta En, means the difference in electronegativity between these two atoms is then equal to 0. Since this equal to 0, that means that these two atoms will be sharing the two electrons in here equally, and thus we will have a nonpolar covalent bond. And now moving on to the next example, the bond between carbon and oxygen. So again, the electronegativity of carbon is 2.5, and for oxygen it is 3.5. So the difference in electronegativity between these two atoms will then equal to 1.0. 1.0 is actually a very big difference in electronegativity, and that would be enough for us, so somewhere in here, so that would be enough for us to classify this bond right here as a polar covalent bond. So going back, we now know this bond right here is a polar covalent bond. And this bond in a polar covalent bond, that basically means there will be a dipole moment on this bond right here. And how will we draw that dipole moment? Would be draw an arrow that they now shifting toward the oxygen atom. Yes, it has to be pointing to the oxygen atom because the oxygen atom is gaining the electron from the carbon. And now don't forget to put in that all the ends of the arrow right there to make it look like half of the positive sign. And now we know that the oxygen is partially negative and the carbon is then partially positive. And moving on to another example, the bond between nitrogen and oxygen. So nitrogen have an electronegativity of 3.0 and oxygen 3.5. So the difference in electronegativity is now 0.5. Since this is 0.5, for the most part, this bond will still be considered to be a polar covalent bond. Now, it would not be as polar compared to the bond between carbon and oxygen. So therefore, as we draw the dipole moment, we would be drawing a dipole moment that again is smaller. And it has to be pointing to the oxygen atom. And now the other end has a half of a positive charge. And in this case, it's slightly partially negative here and slightly partially positive right there. So moving on to another example, the bond between calcium and fluorine. So here in this case right here, the line that I'm drawing right now simply is to show the bond between these two atoms. Now, we normally do not draw this bond right here as a line. And the reason why is because the bond between these two atoms, a lot of time, it actually is not a covalent bond. Why? Well, if we were to be looking at the difference in electronegativity, calcium on our table, its electronegativity is 1.0, and for fluorine, 4.0. So the difference in electronegativity between these two atoms right here is 3.0, which is very, very high, meaning that this bond right here is almost ionic. And because this bond right here is an ionic bond, and we know that ionic bonds do not involve the sharing of electrons. So that's why a lot of time we do not draw this as a line, but rather calcium to be positive and the fluorine to be negative as an ionic bond. So this bond right here, we can say this would be very, very polar covalent or an ionic bond. So I'm going to throw in another example. I'm going to modify this a little bit, and I'm going to change this from a boron to a carbon. And the reason why a CH bond is a bond that we see very commonly in organic chemistry. So it's important that we discuss this bond right here. So what kind of bond would CH be? Will it be polar or nonpolar? Let's determine that. So in this case right here, again, carbon has a 2.5 electronegativity and hydrogen is 2.1. So in this case right here, the difference in electronegativity is actually 0.4, which is basically at the borderline of between polar and nonpolar. But for the most part, we will consider this bond right here to be nonpolar. So remember that if it from 0 to 0.4, it is nonpolar. If it's 0.5 or higher, then that when it be polar. So please commit this to understand this and remember this, because this is a very, very common bond that you will see a whole lot here in this class. And again, commit this to memory and understanding that a CH bond is a nonpolar covalent bond. And lastly, with this one, of course, this bond right here will then be a nonpolar covalent bond. And if we were to now rank them in terms of polarity, then we would then see that this bond right here would then be the most polar covalent bond. It is so polar covalent to the point in which that it will be ionic. But we can call this very, very polar covalent. And the next one will then be this bond right here. So we simply just look at the difference in electronegativity that we have just calculated, followed by this bond, followed by this bond. And now this is the bond between nitrogen and chlorine, and between carbon and carbon are the same. So therefore they both would be equal. So that's how we would rank them, from most polar to least polar. Now moving on to this next subject right here, molecular polarity. What is molecular polarity and how is it different compared to bond polarity? So here in this case right here, molecular polarity is different compared to bond polarity. Molecular polarity refers to the polarity of the entire molecule. So overall, a molecule can be classified as polar or nonpolar, depend on the polarity of the entire molecule. So we have seen that covalent bond, now this is a covalent bond. A covalent bond can be polar or nonpolar. And versus a polar molecule would then be one that actually have a net dipole moment to it. So here's what happened right here. Polar molecules refer to the molecular polarity or polarity of the entire molecule. Overall, if a molecule is polar, that will be a very, very good and a very important physical property that the substance would have, in which that it reacts when or respond when we place it in an electric field. And this because a molecule have many polar covalent bonds, it does not necessarily means that the molecule would then be polar. So what makes a molecule polar? A molecule would be considered to be polar if it has something that we call the net dipole moment. And what is this net dipole moment right here? The net dipole moment is basically the resultant sum of all of the individual dipole moments that the molecule have add together with the geometry taken into account. So that's what the net dipole moment is, the sums of all of the dipole moment add together. Therefore, we call this the net dipole moment. So a molecule can have many dipole moments, and it now dependent on how all of those dipole moments are add together. If they add together to something, that basically means it has a net dipole moment, and therefore the molecule would then be a polar molecule. Whereas if we were to add all of the dipole moments together and now they cancel out, the molecule is then said to have no net dipole moment, and therefore it will not be polar. So two equal dipole moments pointing in the opposite direction will result in having no net dipole moment, and thus the molecule will not be polar. So here is a note right here that is good for us to remember. A molecule can have many polar covalent bonds, but would not be polar if there's no net dipole moment. Let's now try some practice problem to make sure we understand how to determine molecular polarity. So here in this case right here, let's look at CCl4 first. Is CCl4 polar or nonpolar? Whenever we ask that question, it is in the context of molecular polarity. And to be able to answer that question, we have to start all the way from drawing the Lewis structure of the molecule. So here in this case, the Lewis structure of this molecule, as we have seen previously, will be as follows. So in this case right here, the molecule have up to 4 polar covalent bond, right? Because remember that each of this carbon-chlorine bond right here is polar covalent. So this molecule have 4 polar covalent bond. But now, before we add all of this dipole moment together to see if they cancel or not, it's really important that we draw the 3D structure of the molecule, because it is the 3D structure of the molecule that allows us to see how all of this dipole moment add together. So in this case right here, remember that the electron geometry of this molecule right here is tetrahedral. So therefore, that is an important guideline to help us start drawing a 3D structure. Once we know this is tetrahedral already, we will start by drawing the backbone of tetrahedral. And we know that tetrahedral has this backbone right here. So once we have that backbone drawn in already, it is now time to put in the central and the terminal atom. So here in this case, the central atom is the carbon, and we now have one chlorine here, another chlorine here, another chlorine here, and another chlorine here. And now we know each of the carbon and chlorine bond is polar covalent, and the electron will be shifted toward the chlorine. So now let's put in those dipole moment. Here in this case right here, there will be a dipole moment along this bond pointing toward the chlorine. And there will be another dipole moment of the same size as the previous one pointing to this chlorine. And if we were to do the same thing, we're going to draw another one right here and another one right here. Now, the shape of this molecule right here is tetrahedral. Anytime we have the tetrahedral geometry, and if we have 4 of the dipole moment pointing in opposite direction from each other, what will happen is that they will cancel each other out. So in this case, there are 4 polar covalent bonds. But because all these 4 dipole moments right here cancel each other out, there's no net dipole moment. So therefore, the molecule is nonpolar. And nonpolar here refers to the molecular polarity. So going back to this structure here, we can think as the net dipole moment as the force that being pushed or pulled from the central atom. In this case right here, there are 4 forces pointed in this tetrahedral manner from the carbon. So imagine if you were to be the carbon in the middle, and now there are 4 things pointing in this 4 direction from you, and they pull all equally. You will not be going anywhere. So basically, all of the forces are cancelled out. So therefore, the net dipole moment equal to 0, and the molecule is nonpolar. Let's now try another example. CHCl3. So the Lewis structure of this molecule is as follows. And again, we have to draw out the 3D structure of this molecule. And one guideline to draw the 3D structure of the molecule is by first start out with the backbone of the electron geometry. The electron geometry of the central atom here, in this case right here, is tetrahedral. And once we know this is tetrahedral already, we need to draw the backbone of tetrahedral electron geometry, which look like this, as we have seen already. And now we'll put in the central and the terminal atom. So in this case, the central atom is a carbon, and now we have 3 chlorine and a hydrogen. How many polar covalent bonds does this molecule have? Here in this case right here, we will then see that the carbon-chlorine bond is polar covalent, and there are 3 of those, versus a CH bond in nonpolar. So therefore, we can see there will be 3 dipole moment pointing in this direction, and in this direction. So overall, if we were to have these 3 forces right here pulling in this way, will they cancel each other out? And the answer is no, they won't, because they're not flat. These 3 bonds right here are not flat with respect to each other, again because this is tetrahedral. So therefore they do not cancel out, but there is a net dipole moment. And if we were to imagine these 3 forces point down, overall the molecule would be pointing down, and we can think at the overall direction of the molecule as the direction of the net dipole moment. So here in this case, the molecule have 3 polar covalent bonds, but they do not cancel each other out. So therefore there is a net dipole moment. So yes, there is a net dipole moment. And because this molecule has a net dipole moment, it is therefore a polar molecule. Another example with water. Water, the loose structure of water is as follows. So water have 2 polar covalent bonds. And again, we have to draw the 3D structure of water first. So here in this case, again, to draw the 3D structure, start by looking at the backbone of the electron geometry. The electron geometry of the central atom oxygen, here in this case, is tetrahedral as well. So we will start with the backbone tetrahedral. So here in this case, that's what it would look like. And now we will then put in the central and the terminal atom. So the central atom is the oxygen, and now we can put the hydrogen anywhere you want. And here will be 1 lone pair of electron, and here is the other lone pair of electron. And in this case right here, there are 2 polar covalent bonds, and they both pointing to the oxygen, since the oxygen is the more electronegative atom. So therefore, we will be drawing this to the oxygen. If there's 2 forces now pointing to the oxygen, and the bond angle between them is 109.5, will they cancel each other out? And the answer would be no. So therefore, there is a net dipole moment. Yes, there is a net dipole moment. So therefore, this molecule is a polar molecule. And in summary, to determine the molecular polarity, please correct for this, for molecular polarity of a molecule. These are the guidelines and the step that we need to take right here. First, be able to draw the Lewis dot structure of the molecule. Follow by using the Vesper theory, determine the molecular geometry, and let's also add in electron geometry as well. In fact, the electron geometry is more important than the molecular geometry of the central atom. And once we have determined the electron geometry of the central atom already, and we know what kind of backbone it has, we will then be able to draw the 3D structure of the molecule. And the next step would then to identify all the polar covalent bonds and draw the dipole moment in, and know what kind of angle, what would be the bond angle that are pointing or pulling from each other. And the last step, think three-dimensionally and ask ourselves this question. Does the molecule have a net dipole moment? And if the answer is yes, there is a net dipole moment, then that when the molecule will be polar. Versus if our answer is no, there's no net dipole moment, then the molecule will then be nonpolar. Let's now try some of this example. So first one, PF3. Will this molecule be polar or nonpolar? So we have to start all the way from Lewis dot structure. So let's do this. So in this case, phosphorus have 5 valence electron. And now we have 3 fluorine. Each fluorine have 7 valence electron. Adding everything together, there will be 26 valence electron altogether. And because phosphorus can make more bond than fluorine, and it is also present in a smaller amount, therefore we know the phosphorus is the central atom, and the fluorine will then be our terminal atom. So we're going to put them together by drawing this skeletal structure. And again, remember to put the 3 fluorine symmetrically. So far, as we form this skeletal structure, we are using up 6 out of our 26 total valence electron to form this skeletal structure. So that gives us 20 electron remaining. And with the remaining 20 electron, we will then give them 6 to each of the fluorine to complete the octet for the fluorine. And now that's 18 right there. And now we have 2 remaining. So what do we do? What do we do with the remaining 2? Now the answer will be given them to now the central atom to complete the octet for the central atom. So that is the Lewis structure of this molecule. And if we were to now determine the formal charge, all of this atom right here would have a neutral formal charge. And overall, its overall charge is 0 as well. So that will be the Lewis structure of this molecule. And now next, we need to draw the 3D structure of this molecule. So here in this case right here, to draw the 3D structure of a molecule, we need to be looking at the electron geometry of the central atom. And in this case right here, we can see that the electron geometry of the phosphorus will be tetrahedral. Why is it tetrahedral? Because the central atom has 4 electron groups surrounding it. So 3 of this bond and a lone pair of electrons. So overall, there are 4 electron groups, thus tetrahedral. And now let's draw the 3D structure of this molecule. So here in this case, starting with the tetrahedral backbone, we're now going to put in the central and the terminal atom. So here in this case, the central atom is the phosphorus. And now we have 1 fluorine, 2 fluorine, 3 fluorine. Only 3 fluorine. And now let's put a lone pair of electron right there. We do not need to care about the lone pair of electron on the terminal fluorine, since it is not the central atom. So how many polar covalent bonds did this molecule have? And the answer would be 3. Each of the phosphorus and fluorine bond will be polar covalent. So therefore, now we will be having 3 of those dipole moments, all pointing to the fluorine. There's no dipole moment on the lone pair. Please remember that, because there's no bond in there. This would only be a dipole moment if there is a covalent bond. So you can see here in this case right here, although the lone pair do not have a dipole moment, but it's really important. It has a big effect on the overall molecular polarity of this molecule, since the presence of this lone pair electron forces all the dipole moments to be pointing in this way. And in this case, they do not cancel out since they are not flat. So therefore, there will be a net dipole moment, and the net dipole moment will then be pointed down. So there is a net dipole moment, thus this molecule is polar. Its molecular polarities will be called polar. So again, please see the importance of the lone pair of electrons on the central atom, and that how can affect the molecular polarity of the molecule overall. Please try the other example. Let's say now we're gonna try B. So the Lewis structure of this molecule, why don't you take a minute to work on it before we go over the answer together. So what do you have? Is this molecule polar or non-polar? Again, let's follow this step right here. So we need to follow all of this step from 1 to 5 in order to answer this question. So this topic right here combines a lot of things that we have discussed throughout the whole chapter. First, drawn Lewis structure, followed by Vesper geometry, molecular geometry, and electron geometry, and drawn 3D structure, and polar and non-polar covalent bond. So this topic right here covers many other topics together. And to be able to do them, we have to understand many other topics that we have discussed already. So on your next exam, expect something like this. There will be several questions covering this topic where I'll be asking you guys to do the same thing to determine what is the molecular polarity of a molecule. So you have to make sure you know how to do all of this stuff. So now let's go over the answer together. Hopefully you have this Lewis structure right here. So that will be the structure of this molecule. There are 2 lone pair of electrons on the central surface. And now its electron geometry is tetrahedral for the central atom. And now when we draw a 3D structure, it will look something like this. So first start with the tetrahedral electron geometry. And now we're going to put our sulfur, and we're going to put our 1 chlorine right here, the other chlorine right here, and 1 lone pair of electron right here, and 1 lone pair of electron right there. It's important that we also put out those lone pair of electron as well. So that way we can see why the bond angle between these 2 bonds right here would be 109.5. Now in reality, it is slightly less than 109.5. But we, for the most part, we can say it is 109.5. And here in this case, if there's any dipole moment, any polar covalent bond, and we have to go back to this page right here where we can see in this case right here the sulfur is 2.5 and chlorine 3.5. So the difference in electronegativity between them will then be 0.5. So thus the bond is polar covalent, and pointing to the chlorine. There are 2 polar covalent bonds that this molecule would have. And do they cancel each other out? The answer would be no. So then they're not opposite from each other. So therefore, the molecule will have a net dipole moment, and thus it is polar. So here's something for us to remember right here. If we were to have 2 dipole moments, in order for 2 dipole moments to cancel each other out, they have to point 180 degrees from each other in opposite direction. For example, such as that. Or they can also be pointed on this side, point out, or point in. But the angle between them has to be 180 degrees. And if we were to have exactly 180 degrees, that when they would cancel each other out. Whereas if we were to have 2 dipole moments, and now the direction is not 180 degrees, but more or less than that, then that when we would then have a dipole moment. And if we were to have a trigonal geometry, in order for a trigonal geometry to cancel out, they have to be pointing 120 degrees from each other, and that's the bond angle of trigonal planar. And if we would have such, they would cancel each other out, and that would then make this molecule nonpolar. Similarly, we can be having them pointing into each other 120 degrees. And for tetrahedral, in order for tetrahedral to be nonpolar, there has to be 4 dipole moments pointing in the exact opposite direction for them to cancel each other out. If we have only 2 or 3, that when they will not cancel each other out, and there will be a net dipole moment. So hope all of you have now understood molecular polarity and bond polarity. Again, bond polarity refer to the polarity of a bond due to differences in electronegativity, whereas molecular polarity, overall a molecule can be classified as polar or nonpolar, depending on whether or not the molecule has a net dipole moment. And to figure out the net dipole moment of a molecule, we have to follow all of these steps 1 to 5 right here.